us start lecture 5. So, before we do that, I will like to quickly go through some of the stuff that we have already done in lecture 4, for example, some of the concepts. So, here are some, let us quickly go through these. Yeah.
So, if phi is a topology and we do logically invalid of phi, this sentence, is this true or always false? Can this be true or is it always false?
Okay. Logical validity does not belong to the language. Okay. So, it's so you are asking whether if you are asking whether phi a tautology can ever be logically invalid,
yeah.
The answer is no, it cannot be.
Okay.
Yeah.
So,
So look at, I mean, if you look at this validity, for example, the validity symbol is black in color. Okay. So, it is a metalogical symbol. It is a symbol of the mathematics of mathematical logic and is not a symbol of the language of propositional logic. So, whatever is a symbol of the language of propositional logic would be green in color. Yeah, like this phi is green in color, though I am not sure whether you can actually see it, see the color differences clearly here. Okay, so this is, so we defined the notion of logical consequence. So we just say that a proposition phi is a logical consequence of some set of propositions gamma, where this set of propositions gamma is all it could be finite or infinite in general, but most of the time we will think of it as being finite. So, basically if any truth assignment that satisfies all the formulas of gamma also satisfies phi, then you would say that phi is a logical consequence of gamma, right. And when the set gamma is empty, we just call it logical validity. So, essentially what you are saying is that the truth of phi does not depend upon the truth of any other assumptions, for example. Yeah, and so that denotes logical validity, and of course, if you just strike through that symbol, then it denotes invalidity. Yeah, or that it's logic, or that something is logically invalid, or it is not a logical consequence of some of a set of formulae.
Can you give an example of something that is logically invalid?
Oh, you just no. Logically invalid does not mean contradiction. Every contradiction is logically invalid, that is true. Okay, but even almost every contingent proposition is also logically invalid. A contingent proposition is one for which there is at least one truth assignment for which it will be true, and there is at least one truth assignment for which it will be false. So, that is not logically valid, simply because
it can be false.
Yeah, there exists a truth assignment in which all the assumptions are true, there are no assumptions. So, that trivially holds, and the conclusion is false. So any contingent or contradiction is logically invalid. So, we have this notion of logical so we have various, these are actually theorems of these are theorems of the theory of logic, right. I mean, okay. So, and essentially what these theorems tell us is that there is a translation of many of the metalogical concepts into concepts in the language itself. So, in particular, if gamma is a finite set, then and psi is any formula, then psi is a logical consequence of gamma if and only if you can form this huge formula and prove that, and if it is a tautology, then psi is trivially a logical consequence of gamma, right. So, that shows that many of the reasoning concepts that we use can also be expressed within the language of logic itself in some other terms, right. Okay, so the proof for this, as I said, will have to be done through the semantics of by using the semantics of propositional logic, and you please go through this proof. I will not go through it now. Then there are other theorems. For example, here if again gamma is a finite set and then psi is a logical consequence of gamma if and only if this entire sequence of conditionals is a valid formula, is a logically valid formula, which is which is the same as saying that this huge formula should be a tautology, right. And similarly, here is the next one where we construct this entire formula and negate the conclusion and put a conjunction of all of that, and that should be a contradiction. This entire formula should be a contradiction. Yeah. Then we would say that psi is a logical consequence of gamma. So, one thing is of course, a formula is a phi is a tautology if and only if the negation of phi is a contradiction. Yeah. Right. And then we had the notion of logical implication. Now, just like logical consequence, logical implication is also a concept of the theory of logic rather than something within logic itself. Yeah. So, it is not within the language of logic, it only relates to formulae. Okay. So, we would say that phi logically implies psi if and only if phi arrow psi. Now, this is a single formula, right, formed from these are two formulas related by this relation, whereas this is a single formula in the language phi arrow psi, and we are saying that that should be logically valid, which in other words means that it has to be a tautology. Yeah. So, logical implication also can be brought down to the conditional, and similarly there is logical equivalent.
It is only in propositional logic that being a tautology and being logically valid is equal.
Yeah, normally the word the term tautology is employed only for those forms which come from propositional tautologies. Yeah. Okay. In any higher order, in any other logic like first order logic, there are these. So, we are talking about propositional forms, right. So, as I said, P or not P is a tautology. In fact, phi or not phi is also a tautology for any formula phi. Even in any first order logic or any other logic, this form that you have an OR and a positive and its negation on the two sides of the OR, that form, that shape of formula is a tautological form. Okay. So, in the phi in those logics can be some other formula within that logic, but any logic in which propositional logic is some subset, all the tautological forms will be called tautologies there. In addition, they could have logically valid formulas which do not satisfy propositional tautological forms. Okay. So, that is where the difference is going to come. You can think of it as a structure in which you can plug in things, right. So, the phi or not phi, you can think of it as this structure, and in any logic, and you can think of this structure as a tautological form if it takes in some parameter in any logic. It takes in only a single parameter, not two or more parameters, but think of it as a single parameter form in which you can put copies of this anywhere. Then this is always going to be a tautology. It does not matter whether it is propositional logic or first order logic or some modal logics or any other kinds of logics in which are extensions of propositional logic. Okay. On the other hand, when you add other operators in other logics, they might have logically valid forms which do not have this propositional structure. I mean, which are not entirely made up of propositional operators, for example. So, they could, but then they are not called tautologies, they are only called valid forms.
So, any tautology
Not necessarily, not necessarily. The notion of reduction is also something that needs to be formalized. Okay. So, we cannot use that term blindly. If what you are saying is that all tautological forms, all tautologies are logically equivalent to each other, then that is correct. Yeah, that is fine, because you are saying, but that is a semantic statement, right? It's reduction has to do is a proof theoretic statement, it is not a semantic statement. Okay, right. So, this is what we had was logical implication, and its and we had its you have logical equivalence also, which we did, and last time I think we showed that we also so logical equivalence is the kernel of logical implication. So, you take the intersection of implication and its converse, and that common set is the set of all is the equivalence relation on rho naught on P naught. Yeah. The other thing we did last time was that we showed that logical equivalence is a congruence, which boils down to, in any algebraic system, to show some congruence, it boils down to showing that equals the congruent elements are replaceable by congruent elements in any context, and usually that boils down to showing these facts, that in the particular case of this language, it means showing that it is preserved under negation. So, we would say that this relation is being preserved under negation, and similarly we will say that this equivalence relation has to be preserved under these operations. So, these are all binary operations. So, what it means is that you take any formula chi, what you are saying is that, and you take any of these binary operators. So, I am using star to denote any of them, and you are saying that phi star chi should be the logically equivalent to psi star chi if phi is logically equivalent to psi, right. And similarly, so this is like taking a framework and replacing phi which is there in it by psi, and if truth is not in any way perturbed by that, then you would say that it is a congruence relation. Yeah. So, most of our so in the theories of numbers, for example, in real numbers, the notion of equality is a congruence relation. Okay. So, in fact, all your addition, subtraction, multiplication, they all preserve equality on numbers. In the theory of sets, for example, set equality is also a congruence relation. On the other hand, in the theory of finite sets, I could define an equivalence relation which says that a set A is equivalent to a set B if and only if they both have the same number of elements. They need not be the same elements, they have the same number of elements for finite sets. Then it is clear that this equivalence relation is not a congruence, okay, because I can take two sets A and A prime which are equivalent in terms of cardinality, but A union B for an arbitrary B may not be the same as A prime union B, for example. So that equivalence relation is not a congruence relation. So, you have to, for any equivalence relation, it is necessary to determine whether it is preserved under the operators that are of interest to you. Yeah. Okay. So, logical equivalence is a congruence, and that brings us to essentially defining these identities. I mean, this is, so for example, these identities, actually most of them directly come from the equality relation on Boolean algebras. So, what the equality relation on Boolean algebras is a typical example of a congruence, and these identities are essentially linguistic versions of those Boolean identities. So, you can see that. So, for example, for any phi and bottom, phi or bottom is going to be equal to phi. Then there are the usual things, distributive laws, or distributes over and distributes over or. There are the De Morgan's laws, not of or is the not gets distributed and the or gets replaced by an and similarly Then there are these things like simplification and inversion, and there is this negation law, for example. A double negation cancels both of them, right. So, so what this means now is that in any logical context, if you see a subterm of that logical context which can be replaced by another logically equivalent formula, then you can replace it, and that is what we have been using throughout whatever we did in Boolean algebra, in hardware circuits and so on and so forth. So, most of the things that we did, except for in the case of hardware, you have this Carnot map technique, right. If you do not have the don't care states, then what you are doing is you are preserving logical equivalence. But the introduction of don't care states creates a different complication. You are no longer preserving equivalence. You are not, and you are preserving some kind of greater than or equal to relation, but you are definitely not preserving equivalence. Yeah. Okay. So it is important to keep that in mind. So now when you just look at the operators of logic, let us look, there are some other important identities. For example, this biconditional phi biconditional psi is logically equivalent to phi arrow psi and psi arrow phi. I mean, this is something that you can easily prove, and phi arrow psi is logically equivalent to not phi or psi. Now, this is also something that most of you are familiar with. Okay. So, now what we are saying is that in a certain sense these two logical constructs are redundant, okay, in a certain sense. And I would, so given so this omega is all those operators that by which we originally defined propositional logic, right. So, it had top, bottom, not, and, or, arrow and biconditional, for all those operators, right. So, take any set of operators which is a subset of this omega that is said to be adequate for propositional logic if for every formula in P naught there is a logically equivalent formula using only the operators in O. Okay. So, in these two logical equivalences essentially say that if from omega I remove these two operators, the biconditional and the conditional, then what I have left is still an adequate set for propositional logic. Yeah, it is not necessary for me to keep on adding more and more operators, okay, in order to get whatever is the power of those those two constants and those 5 operators. So, that is like 7 operators. Those two constants can be regarded as 2 zero array operators, right. So, instead of the power of the 7 operators is the same as the power of this set without these two operators, the biconditional and the conditional. Yeah. Okay. There is, okay, now this is, so there is another concept that I am going to talk about, and in a certain sense most books on logic do not distinguish between adequacy and that concept which I call functional completeness, but I am going to distinguish between them. Yeah. Okay. So, this is adequacy. So, all I am saying is my propositional logic consists of the two constants bottom and top, a unary operator negation, and the 4 binary operators and, or, conditional and biconditional. And when I look at adequacy of a set of operators, I am looking at it from the point of view of this set. Yeah. So, it is always relative to this set omega, and I am saying that, so a set of operators is adequate for propositional logic if every statement in propositional logic which could be written using all the operators can also be written in a logically equivalent form using this subset of operators. Yeah. So, right. So, from these identities 5 and from identities 5 and 6, what we essentially, and the two simplifications, we get that this set O consisting of these 3 operators is an adequate set of operators, because by the way, it is possible to also get rid of this bottom and top. We do not need them because of the fact that I can choose because of the fact that instead of top I can choose any atomic proposition and write top as P, let us say atomic proposition P, and write top as P or not P, and similarly I can write bottom as P and not P, right, for example. So, even this bottom and top are actually not required. So that which means that with these 3 operators I have an adequate set which captures the expressive power of all of propositional logic up to logical equivalence, right. Further, of course, which you have seen in hardware courses probably, is that you can get rid of one of these 2. Yeah, the De Morgan's identity essentially says that and can be replaced by not and or, right, and vice versa, or can be replaced by not and therefore you just require require negation and one of these, one of and or to get an adequate set. Yeah, okay. And in fact, what you have learnt in your hardware course is that it is not even necessary to have this, it is necessary to just have a single operator, let us say NAND, and that is adequate for all of propositional logic. Okay. Similarly, you can just use NOR. Yeah, but okay, let us live with this. Yeah, since we are interested more in reasoning than in getting minimal hardware circuits, we will keep at least these 3 operators, usually these 3 operators. There is another concept which I am going to define, and that is called functional completeness. Okay. So, you just take this, think of it this way. You take, supposing I define an arbitrary ternary operator on Boolean algebra or on propositional logic, and then I want to know whether that ternary operator is somehow primitive. I mean, okay, so primitive in the sense that is it possible to express things which with that which it is not possible to express with the other operators that I already have, for example. Yeah, this question for some reason most of us never asked. If you take the naturals or take the naturals, yeah, the natural numbers, we usually define these operations like addition, subtraction, multiplication, quotient, remainder, yeah, and essentially we have done all our mathematics with that. However, we are aware that there are functions from the naturals or naturals raised to some power k, there are k-ary functions from n raised to k, which may not be expressible in terms of these 4 or 5 operators that we have got, right. I mean, the class of functions, even the class of unary functions from n to n is uncountably large. We have just limited ourselves to basically these binary operators, yeah, let us say, but that does not mean that there are not functions on the naturals, which it does not mean that every function on the naturals can be expressed up to equality only in terms of these. Okay. On the other hand, Boolean algebra is sort of specially constituted, okay. And that special constitution is that the operators that we have got form a functionally complete set. You take any arbitrary Boolean operator, you define your own arbitrary Boolean operator. Let us say you define a carry Boolean operator from b raised to k to b, where b is the set 0 1. Yeah. Whatever may be the nature of that operator, it can still be written entirely in terms of the set of operators that we already have, and that property is the property of functional completeness.
You are saying this is not true for.
It is not true for n, it is not true for r, for example. In you, I am sorry. Well, min and max may not all be completely defined. Min is defined maybe, but max is not defined always.
No, I am saying min will not be defined. That's what I am saying.
Right, for example. Right. For example, min will not be definable in terms of these 5 operators. Yeah, yeah. There you are. So there are, and you can conceive of other operators which cannot be defined. But in the case of Boolean logic, Boolean algebra, and therefore propositional logic also, every adequate set is also functionally complete. Okay. And the proof for that, actually once you see it, it is actually quite easy. What are we saying? You take this, so what we are saying is, so this property would be true for the propositional logic if it is true for Boolean algebra, right. So essentially the problem, our semantics of propositional logic maps this not to inversion, the Boolean inversion, and to the Boolean product, and or to the Boolean sum, right. So this will be functionally complete if and only if the corresponding operations on Boolean algebra are functionally complete. So in fact the problem reduces to proving that the corresponding operators in Boolean algebra are functionally complete. Yeah. So you take, so let us assume that little o is some arbitrary n-ary operator on the set 0 1. Yeah. So that is it takes it is an n-ary operator which gives you a Boolean result also, it gives you an element from the set, its codomain is also 2, right, I mean the set 0 1, right. So what we are saying is such an operator clearly has something like a truth table associated with it, right. So if you think of this operator applied to n arguments a1 to an, where each of a1 to an takes values either 0 or 1, then there are essentially 2 raised to n different possible sequence vectors of values that can be assigned. And this operator should give you a result, since this is a total function, it should give you a 0 or 1 result for each of those 2 raised to n possible vectors. Yeah. So that is this b, let us say b0 to b2 raised to n minus 1. Yeah. Now, so that means in Boolean algebra, partly because we are talking about a 2 element set, the finiteness of the set is important. In fact, one of the reasons why n to n is you can't get a finite set of functionally complete you cannot get a finite functionally complete set of operators for n to n is because n is infinite, and this number of functions from n to n is uncountably infinite. Okay. Whereas here we are dealing with everything that is finite. So that means there is a table which should tell you for each vector what the result should be, right, and that vector is a sufficient and complete vector, complete definition of this operator or on, right. If there is such a vector, then what I claim is, I claim that this truth table, this is just the truth table, right, for that operator. I claim that this truth table can be expressed in terms of just inversion dot and plus. And how do I express it that way? I just take, I think of this truth table, it has 2 raised to n rows. I can think of this truth table as a big OR of these 2 raised to n rows, okay, of the result of these 2 raised to n rows. Each row I can think of it as a big AND of the individual elements a1 to an, such that take any ai aj, if it is 0 in that row, make it aj bar, because then aj bar will be 1, right. So, it is just a product of those. So, I am calling it aj star. Okay. The star indicates that if aj in that row is 1, then you keep 1. If aj in that row is 0, then basically you are looking at aj bar. Okay. So, I take these aj stars, this product of these aj stars, that is 1, and I take this bi for the ith row. Here again I decide whether I should give that value to be 1 or 0 based on the value of that bi. Okay. So, I have this star at the top here, which will be determined whether it is an inversion or not, depending upon the value of that b at that row. So, I take the product of the individual components in each row and the sum over all the rows, and now that is just a sum of products, right. So, this operator has been completely defined in a sum of products form. Fine, is that clear? Right. So, that shows, now reverting back, that shows that you take any adequate set of operators for propositional logic, that set is also functionally complete up to truth values, right. Okay. Right. The other important concept that we should look at is that we will think of the principle of duality. One of the nice things about your Boolean algebra is really that and also your therefore of propositional logic is that except for these notions like validity and so on and so forth, true and false essentially form have otherwise an equal status. It is possible, at least in Boolean algebra, it is possible to think of 0 and 1 as having equal status. So, it is possible to think of 0 and 1 as being duals of each other. Okay. So, we will say that two formulas phi and psi. So, we are looking at all this in the context not of logical validity, but in the context of logical equivalence, which is a purely algebraic concept, right. Yeah. Okay. So, we are looking at the system of propositional logic under logical equivalence as a simple algebraic system. So, then truth and falsehood are duals of each other and things can be inverted. So, the notion of dual is just this: two formulas phi and psi are called duals of each other. If each formula can be replaced can be obtained from the other by simultaneous replacement of these. So, you replace all ANDs by ORs, all ORs by ANDs, all bottoms by tops and all tops by bottoms. So, you take the formula phi and you get its phi dual. which the tree structure of phi and phi dual, and in fact even the sentential structure is otherwise the same, except that all the operators have been replaced by their duals, right. Now, so essentially this and or are supposed to are duals of each other, bottom and top are also duals of each other, right. But now what happens is that the duality, the two formulas are phi and its dual are not equivalent, okay. They do not even necessarily logically imply each other, but what does happen is that if I take the inversions, okay. So, if I take the negations of the atoms in the dual operator, then I would get the negation of the original formula, right. Is that fine? So, the duality comes through negation. It is a sort of, there is a sort of a mirror reflection that negation does, which gives you the property of duality. It is possible to talk about duality even when there is no negation. For example, you take any set, take the power set of that set under the subset ordering, right. The structure, if you were to draw the, so under the subset ordering you will get, so you take a set S and you have the empty set and you have basically various kinds of subsets in between. Yeah. This structure can be inverted. So, this is let us say under the subset ordering, it can be inverted and essentially under the superset ordering I will get an almost symmetrical inversion which looks the same. Yeah. So, the duality in this case is that every union here will be replaced by an intersection here, subset will be replaced by superset, and every intersection here will be replaced by union. I do not need to necessarily consider inversions at all. For example, I do not need to think of set complements at all. Even with just union and intersection, I get a duality. So, if a set is defined as a union of some other sets, I can think of another set defined as an intersection, you know. But there is an inversion which takes place. So, it is possible to define duality here, but under inversion the duality becomes absolutely precise and exact and the equality becomes notable. Yeah. So, duality does hold for what are known as, this is actually an example of a complete lattice, it does hold for complete lattices too, and once you put in inversions this becomes a Boolean algebra. Yeah. So, then inversions come in naturally, but the point is otherwise the principle of duality does hold for complete lattices which are not Boolean algebras. There is a certain symmetry in the structure which can be inverted, and that is what we mean by duality. Okay. So, this principle of duality for propositional logic is essentially by, you can prove it by structural induction and the use of De Morgan's and simplification laws. Yeah. I am not going to do that. Okay. Once you have logical equivalence, once you have functional completeness and adequacy, and you know that logical equivalence is a congruence relation, you are essentially ready to do things like what you did in hardware. There what did you do? You actually tried to use Carnot maps, for example, to simplify circuits to get the least number of circuit elements, for example, in order to perform a certain function. Well, we are going to work the same way, but towards some system of reasoning. Yeah. Okay. So, the first thing that we will look at is the notion of a normal form. Yeah. Normal forms also exist, also existed in the case of in your hardware circuits, your sum of products forms and product of sums forms were normal forms. Yeah. So, let us look at certain kinds of normal forms. Okay. So, I will take so I will look at my atoms and negations of atoms, right. So, I will call the atoms positive atoms and their negations I will call them negative, and I will call them. So, I will call the atoms positive literals and their negations negative literals. Yeah. Now, a formula is essentially a sentence in propositional logic is in negation normal form if it is built up only from literals using only the operators or and and. Okay. Why is this? Why is it important to look at negation? Look at normal forms? Because then what you are looking at is not the entire language, but an equivalent subset of the original language. So, this way, for example, you take a formula in negation normal form, you are actually removing all those sentences where negation can appear outside and or and so on and so forth. So, you are constraining the language to a smaller set. Yeah. Okay. It is obvious, it is clear that every formula in propositional logic is logically equivalent to a formula in negation normal form. What do? I just use De Morgan's identities to push the negation inside, right, and bring them down to the leaves. There is one thing more also, I need to use that negation law, this one. I will require to use this sometimes to cancel out the negations, though I have not mentioned it. Yeah. So, I will require that, but sorry. Yeah. So, but essentially using De Morgan's identities we can and we can take any. So, one thing is we know that not and or are an adequate and functionally complete set. So, we just consider formulas only using not and or, and wherever not occurs outside somewhere we push it in using De Morgan's laws, right, and if double negations occur we cancel them out. And this process will ensure that every formula is logically equivalent to 1 in negation normal form, which means that it consists of the negation occurs only in front of an atom, it does not occur outside. So, it consists of positive and negative literals, it is made up of positive and negative literals using only the operators and or, that is it. Yeah. The next thing we can do is, this is equivalent to your product of sums form, which I am going to call conjunctive normal form. Yeah. Conjunction is and, disjunction is or. Okay. So, I can take a disjunction of literals. So, I take an or of literals and I take an and of those disjuncts. Okay. And what do I get? I get a conjunctive normal form, which is essentially in what you learnt in hardware, it will come out as a product of sums form. Yeah. So, analogously we can define a conjunction of literals and a disjunction of conjuncts, and that would be what is known as a disjunctive normal form, which in your hardware circuits you came across as sum of products form. Right. Okay. So, but we will call them CNF and DNF, conjunctive normal form and disjunctive normal form. Right. So, the next theorem is again very easy. Every formula in P naught is logically equivalent to a conjunctive normal form. Now, it is enough to assume that the formula is in negation normal form. So, there are anyway no negation signs, all the negation signs when they appear only in front of the atoms. There are no double negations and the rest of the formula is just built up using ands and ors. All you need to do is to distribute the ors over the ands in order to get a conjunctive normal form, and similarly if you distribute the ands over the ors, you get a formula in disjunctive normal form. But there is a price to be paid. Okay. And what is the price to be paid? Ultimately, we have to look at all these things as somehow being part of some implementation in some theorem proving, we have to design algorithms for them and so on and so forth, right. So, what is the price that you pay here? I mean, it is not just pure mathematical theory now. Supposing you have to think of it in terms of what is the price that you are paying, think of algorithms and so on. Your distributive laws create copies. So, take this phi and psi or chi, phi and psi or phi and chi. So, if you have a huge number of ands and ors and you are going to start distributing them, you are going to keep creating multiple copies. In the worst case, supposing you got your formula in disjunctive normal form and you have to convert it into conjunctive normal form by this method, in the worst case you will create 2 copies of every sub formula, which means you suddenly explode the formula to an exponential size by the time you come down to the leaves. Think of it as a tree. Okay. You have a tree of a huge tree, let us say, in which you had disjunctions all over the place up to some frontier, and then you had conjunctions all over the place up to some frontier, and then of course you had maybe some negations scattered, but otherwise everything else is an atom, let us say. Yeah. Now, this is in disjunctive normal form. If you have to convert it to conjunctive normal form, you will be distributing the or over the and, which means you will be replicating nodes, whole subtrees. So, you will get a greatly expanded subtree, which in the worst case can be exponential in size to the original tree, right. So, the use of distributive laws is going to prove expensive in that sense, right. So, but theoretically of course, you just use the distributive laws to convert from one to another, but there is a price to be paid for it. It may not be as bad as exponential because of the fact that it's not it's not the entire tree that it's not that every subtree is going to be replicated, but in the worst case that is the upper bound. Yeah, usually it will be much less, but okay. So, that is one thing. So, that is the price to be paid very often in obtaining a conjunctive normal form, because in obtaining a conjunctive normal form, whenever an or occurs on over an and, you will have to distribute it. So, you will be replicating some subtree in that abstract syntax tree. Yeah. Okay. Right. So, next time what we will do is we will look at how to use these CNFs for the purpose of some kind of verification, validity, proving some arguments right and so on. So, we will look at the design of a tautology checker and then we will look at more algorithms. Yeah. Okay, that will be our first foray with computer science. So, I will stop here.